Hello everyone, let's discuss the efficiency of a transformer. So in order to know the performance of a transformer, we have to calculate efficiency and voltage regulation. So after getting the values of efficiency and voltage regulation, we have to get the information about the performance of a transformer. So generally, what is the formula for efficiency? Output power by input power, right? P input. So, and the input power is nothing but what? Output power plus losses. Output power plus losses. So we all know that. What is this E2 I2 cos phi 2? This output power can be calculated as kVA rating of a transformer, which is multiplied by power factor of load, that is suffix 2. We all know that the nameplate details which are mentioned are nothing but with respect to load only, right? E2 I2, that's why it is equals to E2 I2 cos phi 2. That's why output power is E2 I2 cos phi 2 by E2 I2 cos phi 2. And what about this IT square R02? These are nothing but copper losses and these are nothing but iron losses, right? Okay, this is the formula for efficiency. But what is the formula for efficiency at different fractions of load? So during operation, we may get full load or fractions of load. The load current may be different fractions, right? Maybe it should be half of the full load, it should be 3/4 of the full load, maybe it should be 1/4 of the full load, that is 25 to 50%, 50 to 75%, like that. Any fraction of load, for any fraction of load, the formula for efficiency is nothing but what? Which is equals to E2, in place of I2 you have to write X into I2, fraction of secondary current, which is by E2 X I2 cos phi 2. And what about copper losses? We all know that X into I2 whole square into R02. With the variation of load current, obviously copper losses are also varies, that's why X into I2 whole square into R02, that's why this is square into PCU, right, plus PI. This is the formula for efficiency at different fractions of load. So we all know that this is the formula of efficiency at different fractions of load. And in this, what are the variable parameters? What are the variable parameters? Current is variable 1 and the frequency is variable 1, because with the variation of the load, the power factor of the transformer changes. What about E2? This is present nameplate detail, right? So only I2, fraction of load current, and that is fraction of load current and cos phi 2 are varied during operation, right? That's why we have to get the condition for maximum efficiency. For that, current, when the current varies, we have to keep power factor as constant. That is the first case, that is differentiation of efficiency with variation of load current when phase angle is constant. What is that meaning? Power factor is constant. And second one is what? Variation of efficiency when with the variation of phase angle keeping xi2 constant. So we have to get these two cases. These two cases are required to get the condition for maximum efficiency. First I would like to go with case 1, later I have to discuss this case 2. First, the efficiency is with respect to xi2 keeping phase angle constant. This is the first case. So this is the efficiency formula, and in order to differentiate this with respect to xi2, we have to use U by V formula, right? u by v. So with respect to dxi2, which is equals to 0, right? Therefore so this total term, this is denominator, right? This is numerator. So we all know the denominator power whole square should be equals to 0. Then upper part should be x into e2 i2 cos phi 2 plus x i2 whole square into r02 plus pi, right? Which is multiplied by differentiation of this numerator, that is with respect to xi2, this is equals to what? e2 cos phi 2. Clear? So later minus x e2 i2 cos phi 2, which is the differentiation of this denominator. Denominator is nothing but what? We have to get e2 cos phi 2 from this e2 cos phi 2 with respect to xi2, and 2 into xi2 r02, right? What about this iron loss component? That is constant, therefore that is treated as 0. With respect to xi2 only we have to differentiate, which is equals to what? 0. From this term should be equals to 0. Therefore the only component which is present is nothing but what? X e2 square i2 cos phi 2, right? Like that, plus x i2 square r02 e2 cos phi 2 plus pi e2 cos phi 2 minus, you have to get x e2 square i2 cos phi 2 and then minus 2x square i2 square e2 cos phi 2 r02, which is equals to 0, right? So from this we have to take e2 square, this one and this one gets cancelled, and e2 cos phi 2 e2 cos phi 2 is gets common, right? e2 cos phi 2 is gets common, that's why xi2 whole square into r02 plus pi minus 2 xi2 whole square into r02, which is equals to 0, right? Because e2 xi2 gets common. So from this is equals to 0, right? This is equals to 0. From this we are going to get what? xi2 whole square into r02 plus pi, which is equals to 2 into xi2 whole square into r02. From this pi should be equals to what? X into i2 whole square r02. These are nothing but what? It's a square into i2 square r02, right? What is this? It's a square into PCU, that is pi should be equals to x square into PCU. What is the condition? To get maximum efficiency, iron loss should be equals to copper loss, right? that is iron loss should be equals to copper loss. Then only we are going to get the, at that condition only we are going to get the maximum efficiency, where x is nothing but what? Fraction of full load. For example, if x is equals to 1, obviously Pi should be equal to PCU, right? At full load, at full load, iron loss should be equals to copper loss. At full load condition, what is the condition to get maximum efficiency? Iron loss should be equals to copper loss. So this is the condition. The maximum efficiency in transformer will be obtained only when what? Copper loss should be equals to iron loss. Copper loss should be equals to iron loss. So we all know that x square into this is nothing but PCU, that is WCU, this is iron loss component. So from this we have to calculate the value of x, right? Fraction of load which is corresponding to maximum efficiency. So from this x square into WCU should be equals to Wi. From this the value of x is nothing but what? Square root of iron loss component by copper loss component, which is nothing but what? Fraction of s which is corresponding to maximum efficiency. Fraction of x which is corresponding to maximum x. Corresponding to maximum efficiency. Clear? We all know that XI2 is nothing but what? Secondary load current at different fractions. So let us take XI2 should be equals to I2M. XI2 should be taken as I2M. So from this we all know that XI2, what is this? XI2 whole square into R02, which is equals to iron loss component, right? So from this, in place of XI2 you have to put I2M. Therefore I2M square into R02, which is equals to iron loss component, right? This is the component. So from this, this is the current, secondary load current, which is corresponding to maximum efficiency. Secondary load current which is corresponding to maximum efficiency is nothing but what? Square root of iron loss component by resistance. So from this condition we have to calculate fraction of x corresponding to maximum efficiency, like that. Secondary load current corresponding to maximum efficiency we have to calculate. For this, what is the formula? It is equals to x, which is equals to Pi by PCU. For this, what is the formula? I2M, which is equals to square root of Pi by R02. Okay. So what is the formula? I2M, which is equals to what? Square root of Wi by R02. Let us multiply with secondary terminal voltage I2M, which is equals to E2 square root of iron loss component by R02. Okay. So from this I2M which is equals to, can I write like this? E2 I2 by I2, right? E2 I2 by I2, that is I2 divided by with I2. Obviously we are going to get the same value, which is equals to Wi by R02. So from this E2 I2M should be equals to E2 I2. Can I write like this? I introduce this I2 into this square root. Obviously we are going to get I2 square R02. So we all know that I2 square R02 is nothing but what? E2 I2M, which is equals to E2 I2 into this is what? Iron loss, and this is what? Copper loss. So this is what? Load kVA corresponding to full load corresponding to maximum efficiency. Load kVA corresponding to maximum efficiency. E2 I2 is nothing but what? Full load kVA, square root of iron loss by copper loss. This is the formula for this. That is, this is what? Load kVA corresponding to maximum efficiency. So we have derived fraction of load corresponding to maximum efficiency, square root of Pi by PCU. Secondary load current corresponding to maximum efficiency, square root of iron loss component by R02. Like that, load kVA corresponding to maximum efficiency, which is nothing but what? Full load kVA into square root of Pi by PCU. And we all know that this is the efficiency formula, and from this we have to write the equation like this. We have to divide this equation with x E2 I2 cos phi 2, right, in numerator and with denominator. Finally we are going to get, this should be like this, right? That is, these are nothing but what? Losses. These are nothing but losses. This is nothing but what? Power. So finally these are nothing but losses in the transformer, and this is what? Power in the transformer. The ratio is nothing but what? Losses in transformer by output power, right? So from this, what is the relation we have to get? Efficiency at x of full load should be equals to 1 by 1 plus losses by power, right? This is the relation. So the efficiency of transformer depends on losses to output power ratio. If losses to output power ratio is very high, let us take this ratio is very high, what will happen to efficiency? Obviously the efficiency is decreases, right? That is, if losses to output power is increases, what will happen to efficiency? Efficiency at x, what will happen to efficiency? Efficiency at x of full load is obviously decreases. If losses to output power is decreases, obviously what will happen to efficiency? This is increases. Simple. If losses to output power increases, efficiency decreases. If losses to output power is decreases, efficiency increases. Okay. So for this, this is the relation. For this, this is the relation. So in this case, first the variation is what? Load current XI2 versus efficiency and losses to output power. Efficiency versus XI2 and losses by output power versus XI2. But we all know that if output, this losses to output power is very low or very high, see it is very high, obviously what about the efficiency? The efficiency content is very low, right? Losses are more, efficiency is very low, that's why it is from 0 to some extent. But when the losses to output power is minimum, right, this is the minimum position. In this case, what about the maximum efficiency? This is the maximum efficiency condition. Later the losses to output power ratio is what? Again increases, obviously the efficiency is decreases. So efficiency and losses to output power is inversely proportional. If this is maximum, here we are going to get minimum efficiency. This is the minimum, we are going to get maximum efficiency. So this is maximum, this is minimum. Here this is minimum, this is maximum. This is about to maximum, obviously this is reaching to minimum, inversely proportional. Then how can we get these observations? Here copper loss content is less than Wi. At this position See, at this instant only, what is the instant? Copper loss content should be equals to iron loss component. Like that, copper loss component should be equals to iron loss component. This is the point. At this point only, we are going to get the maximum efficiency. This is the maximum efficiency, right? But because the load variation is changes, that is xi2 is low, such that what about copper losses? C square I2 square R02 are less than iron losses. That's why WCU should be less than WI. That's why this is the case. From here to here, we are going to get the condition. This is first one. Second one, xy2 is such that xi2 whole square R02 should be equals to Wi. That is WCU should be equals to Wi. This is the case. In this condition only, the efficiency is maximum. Later, xi2 is very high, increases. So previously it is low, now it is increases. Now xi is very high, such that xi2 whole square R02 is more than Wi, right? That is nothing but what? Copper loss content is more than iron loss content. Then what about efficiency now? In this case, efficiency is what? Minimum, right? When copper loss content is less than iron loss content, obviously the efficiency is minimum. What about loss to power ratio, which is nothing but maximum. Clear? If the load current is increases such that the copper loss content should be equals to iron loss content, there you have to get maximum efficiency. Like that, what about loss to power ratio? This is minimum. So again we are going to increase this xi2, that is fraction of load is increases. What will happen? Again efficiency is what? Minimum. So for the value omega cu which is less than iron loss component, the copper loss content which is less than or increases iron loss component which is more than or less than iron loss component, we are going to get less value of efficiency, that is losses to power should be equals to maximum. These are the very important observations, right? So based on this we are going to get the efficiency versus load current and losses to output power versus load current. This is about variation of efficiency with load current. So obviously the efficiency curve with respect to load current is double valued function. That's why the same efficiency is possible at two different load. So this is the let us take, and this is half of the load. Let us take half of 1/4 of full load. Let us take, or you can say x1 of full load, right? It's better because we don't have any scaling, right? Because this x1 of full load, this is what? x2 of full load. At these two loads we are going to get the same efficiency, that is approximately 98%. That's why the efficiency curve versus with respect to load current is double valued function. That's why we have two load conditions. This is about the case 1. What is case 2? Change in efficiency with respect to power factor keeping xi2 constant. Keeping xi2 constant. So what is the equation for us? Should be equals to what? E2 I2 cos phi2, that is x E2 I2 cos phi2 by x E2 I2 cos phi2 plus c square PCU plus Pi, that is efficiency with respect to, right, which is equals to numerator part should be equals to 0. That's why directly we have to write. Of course we have know that the differentiation of this with respect to into what? this part, right? Minus x e2 I2 cos phi 2 is nothing but sin minus sin phi 2. That's why minus sin phi 2 minus, again you have to write x e2 I2 cos phi 2, which is minus e2x I2 sin phi 2. What about this? These are constant, therefore 0, which is equals to what? 0. So from this, what we have to get? So from this, minus c square e2 square I2 square, right? e2 square I2 square cos phi 2 plus or minus s square pcu plus pi into x e2 I2 sin phi 2, which is equals to this part, right? Now it is plus, after getting this side, x square e2 square I2 square, sorry, here we have sin phi 2 also, cos phi 2 sin phi 2, which is equals to, sorry, no 0. So from this we are going to get this part gets cancelled, right? Therefore only component we are going to get is nothing but minus s square pcu plus pi into x e2 I2 sin phi 2, which is equals to 0. Therefore the entire part from this side to this, which is equals to 0 only the term should be present, sin phi 2 should be equals to 0. Therefore phi 2 should be equals to 0. What is the condition? UPF, that is the power factor is UPF at maximum efficiency. What are the conditions to get maximum efficiency? Iron loss component should be equals to copper loss component, and second condition is what? At maximum efficiency the power factor is nothing but unity power factor. We have unity power factor. This is the second condition. So we all know that this is the relation between losses to output power should be equals to what? Losses to the output power, and this is the graph with respect to losses versus output power and cos phi 2. If power factor increases, let us take previously this is decreases, cos phi 2 decreases, what about this? Losses to output power is increases gradually. Let us consider the power factor is increases. What about this? Losses to output power decreases. See, initially the value of power factor is very low, that's why losses to output power is what? Very high. If cos phi 2 is 0, if cos phi 2 is equals to 0, losses to output power should be equals to infinite. That's why it should be start from infinite, that is losses to output or losses to P out is inversely proportional to the power factor, right? Now it's clear. So if this is increases, obviously the losses to output power is decreases. That's why by increasing the value of power factor from 0 to UPF, the losses to efficiency curve is decreases. But we all know that losses to output power is inversely proportional with efficiency also, right? So by increasing the power factor, the efficiency also increases, that is cos phi 2 is proportional to with efficiency. See, for the low value of power factor, what is the efficiency of the transformer? Very low. We are gradually increasing the power factor, it is reaching to maximum value. After some point it is reaching to maximum value. What is the condition? Keeping excited constant by varying power factor. What is the condition 1? Keeping power factor constant varying Xi2. But what about the efficiency depends upon the power factor? No. By keeping load current constant, if load power factor is varied, efficiency is maximum exactly at UPF. So at UPF only we are going to get the maximum efficiency. The power factor, whether it is leading or lagging, efficiency is same for lagging and leading power factor, and it depends only on the magnitude of power factor. Only it is dependent on the magnitude, but not nature. Whether it is lag or lead, it is only depends upon magnitude of the power factor, magnitude only, right? It is only depends on magnitude of power factor. This is about the efficiency of transformer, and we all know that these are the main observations. This is the curve between what? Copper loss content less than iron loss component, up to what? This point only. This is the point where copper loss content should be equals to iron loss content, and this is the point, this is the region where copper loss content is more than iron loss content, right? At this point we are going to get the maximum efficiency. What about this point? Losses to P out is minimum, right? When it is minimum, the efficiency is maximum. Then this is the point where iron loss component should be equals to copper loss component. So these are nothing but iron losses. See, this blue color marker represents what? Iron loss. Those are nothing but constant losses. That's why there is no variation in the graph for constant losses, that is constant from zero losses to maximum losses. But what about this red color marker? These are nothing but variation of copper losses with the variation of Xi2. Initially the load current is very low, that's why the copper losses are very low, right? That's why if we increase the load current, gradually the graph of copper loss is also increases. So in this, from here to here, this magnitude is very less compared to this magnitude. That's why copper loss is less than iron loss. At this point both are equal. After this component is more than iron loss component. So these are the graphs representation of different parameters, and this is the graph between power factor, efficiency and Xi2. So for 3, so efficiency on y-axis, load on x-axis, and in this graph we are going to get for low power factor 0.4 power factor, 0.6 power factor, 0.8 power factor. At UPF we are going to get the maximum efficiency. So this is the representation of 3. Efficiency curve with respect to variation in load current and load power factor. So these are the very important graphs. Now we have to discuss the very important observations. So for example, if iron loss should be equals to 100 watts, copper loss should be equals to 100 watts, right? And the question is, then maximum efficiency is obtained when only when what? When, what is the condition? WI should be equals to WCU, or power factor should be equals to unity. Only for these two conditions only we are going to get the maximum efficiency. But the given data is what? That is, from the given data, efficiency maximum is achieved, right? Because iron loss component is 100 watts, copper loss component is 100 watts. Obviously we are going to get the maximum efficiency. At this condition only we are going to get the maximum efficiency. This is about first observation. Second problem, if iron loss is for example 50 watts and copper loss component is for example 150 watts. Question is then what are the components of Wi and WCU at maximum efficiency? What are the components or what are the content of Wi and WCU at maximum efficiency? For this, what is the answer? We all know that for maximum efficiency, what is the condition? Iron loss component should be equals to copper loss, right? Therefore, iron loss component should be equals to what? 50 watts only, and copper loss component should be equals to 50 watts. What is the reason? Because iron loss component is constant losses. Iron loss are nothing but what? Constant losses, and copper loss are nothing but what? Variable losses. What is the reason here? These are nothing but constant loss. What about this? This is variable loss. That's why the copper losses are reaching to 50 watts only. Then only we are going to get the maximum efficiency. Therefore, this is the data. Iron loss component is what? 50 watts. Copper loss component is nothing but what? 150 watts. So, what are the components of iron loss and copper loss at maximum efficiency? We all know that the condition for maximum efficiency is nothing but what? Iron loss component should be equals to copper loss component, or power factor should be equals to unity. But the given data is with respect to losses only. Therefore, to get maximum efficiency, the iron loss component should be equals to copper loss component. But we all know that iron loss are nothing but constant losses. There are no changes in the copper losses. The only changes that we are going to happen, that we are going to get, is nothing but copper losses only. That's why the copper loss content should be equals to 50 watts. Iron loss component content should be equals to 50 watts only. And next question is, if Wi should be equals to 150 watts and copper loss content should be equals to 50 watts, then question is, then what is the total loss in a transformer at maximum efficiency? What is the total loss in a transformer at a maximum efficiency? So we know that at maximum efficiency, iron loss component should be equals to copper loss component. Therefore, what about iron loss component now? Therefore, Wi should be equals to what? 150 watts. What about WCU? Which is also 150 watts only. Therefore, total losses are nothing but what? Wi plus WCU, which is equals to what? Wi only, right? Because iron loss are nothing but constant losses, copper loss are nothing but variable losses, which is equals to what? Wi plus Wi, which is equals to 2Wi. These are the total losses in a transformer. What is the condition? Must and should condition. Total losses in a transformer at maximum efficiency, because there is change in the copper loss content, there is no change in the iron loss component. That's why Wi, this two should be equal. Why? When these two are equal, then only we are going to get the maximum efficiency. Therefore, total loss component at maximum efficiency is nothing but what? 2 times of the iron loss component. Therefore, answer is what? total losses, which is equals to what? 2 into Wi, which is equals to what? 2 into 150. The answer is what? 300 watts. Not 150 plus 50. The total loss component is not 200 watts. It is equals to 300 watts at maximum efficiency. This condition is must and should. This condition is must and should. Only at maximum efficiency only the total loss component is nothing but 2 Wi. These are the very important observations. This is about the concept of efficiency.